No, I forgot. So if we want to find the slope of a parametric equation, then we do dy. We take the derivative with respect to our parameter of the y, derivative with respect to our parameter of the x. So if we look at this one, well, x was 3 cosine. Y was 2 for sine. So if we do dx dt, the derivative of x with respect to t, let's see, that's 3 times the derivative of cosine is what? Negative sine, so minus sine t. We take the derivative of this one with respect to t, we get dy dt equals 4, the derivative of sine, cosine. So our slope, dy over dx, is dy dt over dx dt. So let's see if that generates the correct slope. So if we look here, our t turned out to be pi over 2. So let's find our slope at pi over 2. If I do cosine of pi halves over negative 3 sine of pi halves, what's cosine at 90? 0. Sine of 90 is 1. 0 over negative 3 is 0. Which is what we suspected. We suspected that up there at the top, we had a horizontal tangent line. Yeah. What was the p over there? Pi? So if we want the slope at pi, what's cosine at pi? Or negative 1. What's sine at pi? 0. So we get something over 0, which is undefined. What kind of tangent line do we have on the left side? Yeah, we have a vertical one. What's the slope of a vertical line? Undefined. The slope of a horizontal line is 0, but the slope of a vertical line is undefined. In the past, most everything we've dealt with have been functions, so we didn't have vertical tangent lines. Now, when we had implicitly defined functions, we did have some graphs that were not functions, so we did have some. But with parametric equations, you have all sorts of graphs that aren't necessarily functions. So we can have vertical, undefined tangent lines. If we were to let t be any number, we could find that for what t's would our slope be 0? And if we look at this, this will be 0 anytime our numerator is 0. This will be undefined anytime our denominator is 0. So if we were looking for what t values would give us a vertical or a horizontal tangent line, we could find those. Now, that's not so bad for our first derivative. Let's look at the second derivative. If we want excuse me. trying to see how I want to say this. So if we want our first derivative, that's dy dt over dx dt. If we want our second derivative, that's basically the derivative of our derivative. So that's the derivative of dy dt over dx dt. And basically what we can do is we can take the derivative with respect to t. If you rearrange these. If you have the first derivative, we're going to take the derivative with respect to t of our first derivative, and then we're going to divide that by dx dt. So once we get our first derivative, we're going to take the derivative of that with respect to t, divided by dx. So I'll just take this off to keep from confusing us too much. Do what? Yeah. If we want the third derivative, then we would take the derivative with respect to t of our second derivative divided by dx dt. So we basically take the derivative of our previous one with respect to t, then take the derivative of, then divide that by dx. So they give an example in the book. They say, let's suppose x equals the square root of t, y equals 1/4 t squared minus 4. Yeah, you take the derivative of the second derivative with respect to t, and then divide that by dx. So they say, find the slope and concavity at the point 2/3. So that brings up an interesting question. So at that point, at the point 2, 3, we need to know what t is. So notice x is the square root of t. So when x is 2, what would t be? What t would give you an x of, 4? Square both sides. So in order for x to be 2, t would need to be 4. Notice if we put a 4 in here, 4 squared is 16, minus 4 is 12. What's 12 divided by 4? 3. So yeah. So if we want the slope, we need dy over dx. So we need the derivative of this with respect to t, and the derivative of x with respect to t. I is 1/4 times t squared minus 4. Then dy dt, if we take the derivative of that with respect to t, 1/4 is a multiplicative constant. What's the derivative of the parentheses? 2t. The 2 and the 4 reduce, giving us t over 2. So that's dy over dt. X is the square root of t, also known as t to the 1/2. So what is dx dt? Right, 1/2 t to the negative 1/2. Or if we move the t to the negative 1/2 to the denominator, that's 1 over 2 square roots of t. So dy over dx is this one divided by that one. Of course, if we're dividing by a fraction, we can also multiply by the reciprocal. So basically, that's the slope. You tell me what t is, I'll tell you the slope. So at that point, 2, 3, what was our t? 4. So at t equals 4, our slope is 4 square roots of 4, or 8. Square root of 4 is 2, 2 times 4. So that's our slope at that particular time. If we want our concavity, what tells concavity? The second derivative. So if we want the second derivative, we need to take the derivative with respect to t of our first derivative. So let's take our first derivative and let's rewrite that. Our first derivative was t square roots of t. Notice that's t to the first times t to the 1/2. What do you do with the exponents when you're multiplying like bases? Add them, so that's t to what power? 3/2. So if we take the derivative of that, what's that, 3/2 t to the 1/2? Or 3/2 times the square root of t? Or you could call that 3 square roots of t over 2. So for our second derivative, we're going to do that. Divided by dx dt. Dx dt. 1 over 2 square roots of t. So 3 square roots of t over 2 times 2 square roots of t over 1. What does that simplify to? 3t. Square root times itself, square root squared, so the square root squareds cancel. So if we want the concavity at t equals 4, the second derivative at t equals 4, 3 times 4 is 12. Right, that's positive, so that, yeah, that'll be concave up. Pretty similar, perhaps. So that's finding slope, concavity. Remember that in order to find arc length was the square root of 1 plus dy over dx squared dx. It's still 10.3. So if we think about dy over dx being dy over dt over dx dt, if we square that, then we have dy squared dt over dx squared dt. And when we solve that, simplify that, it turns out that our arc length becomes dx dt squared plus dy over dt squared under the square root dt from A to B, where if this is t, then A and B are t values. So let's look at an example. Well, it basically comes from if we distribute through by dx over dt squared, then we'll have a dx over dt squared here. The dx over dt squared here cancels out. When we move that outside, if we multiply on the inside by dx over dt squared, then we have to divide on the outside by dx over dt. So the dx is canceled, and you have dt. Because basically you have dx over dx dt, which is dx times dt over dx. So those cancel. So that's how we get dt on the outside. So let's see. Let's do this one. X equals 6t squared. Y equals 2t cubed. 10.3 still. And let's look from t equal 1 to t equal 4. So let's look at the arc length. So this is some parametric curve. We don't even have to know exactly what it looks like. These are our parametric equations. We can put a 1 in, and we can get a point. We can put a 2 in, 3 in, 4 in, and we can kind of sketch what our curve would look like. And I guess we'll do that for practice. Yeah, we went from 1 to 4. Actually, when we get, I don't need this grid because this is going to get big in a hurry. This is t. If we put a 1 in for t, we get 6, 2, not 6t. If we put a 2 in, we get 4 times 6 is 24. 8 times 2 is 16. If we put a 3 in, we get 9 times 6, 54. 27 times 2 is 54. If we put a 4 in, we get 16 times 6, so 96. 64 times 2 is that 128. So over time, the y value is starting to catch up with the x. So if we just kind of roughly sketched it. To begin with, we're farther to the right than we are up, and over time, we're going to get to where we're higher than we are to the right. So something that's curving like that. We start here, we're moving in this direction until we get up to here. We're 96 to the right, 128 up. So we're basically looking for the length of that curve. And on the test, if I ask you to make a plot, I do want to make sure you have the arrows in. Show me where your parametric curve starts and where it stops. Because it starts at t equal 1, it stops at t equal 4. So if we want the arc length, we need dx dt. So what's dx dt? 12t. We need dy dt. What's dy dt? 6t squared. We need each of those squared. So what's that? 144t squared. And then 36t to the 4th. So our arc length is the integral from t equal 1 to t equal 4, the square root of dx over dt squared, plus dy over dt squared dt. Now inside, do these terms have anything in common? T squared, they also have something else. Doesn't 36 go into both of those? $36 goes into that 4 times. 36 goes into that once. Pull a t squared out, we're left with a t squared. So notice we have a product. When you take the square root of a, you can take the square root of those separately. So if we take the square root of the first part, the square root of 36, the square root of t squared, we get that. That 6 is a multiplicative constant. We can pull it out front. And I'm going to put the t over here at the end. What do we need to let u be? Yeah, 4 plus t squared. So that means du is what, 2t dt? So if we call that u, then what are we missing here? 2. So if I multiply by 2, I also divide out front by 2. So that's 3 times the integral of the square root of u, or we could call that u to the 1/2. That part is du. And let's just go ahead, instead of integrating and then changing back to t, let's change these t's to u's. This, remember, this is a t value, but this tells us how u and t are related. So when t is 1, what would u be? Yeah, 1 squared plus 4. So when t is 1, u is 5. When t is 4, what's u? 20. So our arc length is 3 times, integrate u to the 1/2, so that's u to the 1 bigger power over that power, evaluated from 5 to 20. So notice, instead of dividing by 3/2, we can multiply by 2/3. So the 3's cancel, so that's 2 times, plug a 20 in, 20. If we're doing something to the 3/2, we're taking the square root of that and cubing it. And then minus 2 times, put a 5 in, we're taking the square root of that and cubing it. Well, turns out 20 and 5, neither one are perfect squares. So if we convert that to a decimal, we've got the square root of 20 cubed times 2 minus the square root of 5 cubed times 2. Is that about 156.5? So it's just basically being able to manipulate that formula.
4 plus 2 squared, or there will be made 4 plus 2 squared. What is that back? Yeah, put it back in. But you don't have to. You just set it out.
Yeah. So we could have done it 2 ways. We could have, once we integrated, we could plug that in for u and then use 1 for t and 4 for t. Or we could have left it. Since we were doing a definite integral, we were looking for what does that come out numerically. We weren't looking for a function. So it doesn't matter if we get u's or t's or what. So we could have, once we got this, put 1 plus t squared in, or was it 4 plus t squared, and then put 1 and 4 in, or we could have just left it in terms of u and change our t's to u's. All right, so that's the main things out of 10.3 that you need. The first part of 10.4 we've done back in trig, polar coordinates. And remember when we have a rectangular grid, we have x and y. But we can convert a coordinate on there to r and theta, where r is the distance that that point is from the center, theta is the direction. So in terms of x and y, this distance is x, this distance is y. So if we want to relate x, let's see, let's actually do this. R, if we want r, x squared plus y squared, x squared plus y squared is r squared. If we want theta, is the y coordinate over the x coordinate. So if you're given an ordered pair, these relate your ordered pair to your r and your ordered pair to your theta. Now, if you're given r and theta, and you want to change it back to a rectangular coordinate, notice that if we try to find x, cosine of theta is x over r. So that implies that x is r cosine theta. Sine theta is y over r, which that implies that y is r sine theta. So those are some more formulas I put on my formula sheet. And in general, these take you from rectangular to polar coordinates. These take you from polar to rectangular coordinates because notice if I put an r and a theta in, it tells me an x. Put an r and a theta in, it tells me y. So I take what I start with, put them in, and that gives me rectangular. Or I put in rectangular and it gives me a polar. Put in rectangular, it gives me a polar. So I'm not going to go back over everything in here because a lot of it is just straight up trig. But we will go back over graphing some polar equations. For example, if we're asked to graph just the polar equation r equals 2, I'll pull up a polar grid. If I want to graph r equals 2, notice there's no theta in this equation. So that means no matter what angle I pick, you give me an angle, r equals 2. You give me another angle, r equals 2. Any angle you go to, r equals 2. So if I go to every angle and plot a radius of 2, that's going to be nothing more than a circle centered at the origin. If I say, let's plot theta equals pi over 3. If I were to make a table, that means no matter what radius you tell me, I'm going to plot that radius in the direction of pi over 3. So that's going to be a straight line in the direction of pi over 3, which pi over 3, that's 60 degrees. Remember, we can also have a negative radius. If I'm in the direction of pi over 3 and I have a negative radius, that means to go away from pi over 3, so that's in that direction. So that's just a straight line there. If you say, let's graph r equals cosine theta, you could just make it simple. And you could do a lot of different angles. Plot the corresponding radius. So if in the direction of 0 degrees, our radius is 1. 90 degrees, we're at 0. 80, we're at negative 1, 2. Now, it turns out that's really not enough points to show us what's going on here. In the direction of 0 degrees, we're out 1. In the direction of 90, we're actually not out any. In the direction of 180, we're back to here. In the direction of 270, we're not out here. I'll give you a handout, and it turns out that that's actually, if we were to pick enough points, that would get us a circle just on the right side of the origin.
0 and 1.
Between 0 and 1. Basically, the coefficient here tells us the diameter. I gave y'all, for those of y'all that had me for Math 113, I gave y'all that handout. And it had lots of different things. It had It had cardioids on it, which are things that kind of look like a lily pad. Looks like some of them look kind of like a heart. I mean, that's what the cardioid.
Yeah, I've seen that polar, waves. I've seen that really bad thing.
Yeah. So I'll give y'all this handout. If you remind me, I'll give it to you after class. So if we want to graph something, for example, r equals 3 minus 2 sine theta. Anything that's of the form r equals a plus or minus b sine theta or cosine theta, either one. If we a constant plus or minus another constant times cosine or sine, as long as it's 1 theta here, then it's going to be one of these 4 general shapes. It's going to be a cardioid, a limicon. Cardioids are particular limicons. It's going to be a cardioid, or it's going to be a limicon like this, or like this. And the way we differentiate between which of these 4 it is notice underneath each of these graphs we have A over B, where A is the constant, B is the coefficient of the sine or cosine. So on ours, A is 3. We just take the number. We don't take the sign with it. So B is 2. So A over B is 3 over 2. So we go back to our handout and we see which one of these is A over B 3/2 fit. So 3/2 is 1.5. So we want the graph that's A over B is between 1 and 2. Now, we have to keep in mind, that doesn't mean our graph is going to perfectly be shaped like that or turned like that. It could be bigger, it could be smaller, it could be rotated, but it is going to have that generic shape where we don't go through the origin. Instead of having a sharp bump right here, we have a little bit more of a subtle bump. These two are equal distances from the origin. This is noticeably different from this.
It should become like
Yeah. Yeah. And the different ones do have more specific names for them. But to be honest, I don't remember all of those.
Yeah, I've seen it showing you this.
Oh yeah, yeah. So the way we get the direction those are turned is we need at least 4 points. And I'll just use our quadrantal angles, 0, 90, 180, and 270. Just real quickly, if we put a 0 in, we get a radius of 3. If we put a 90 in, we get a radius of 1. 180, we get a radius of 3. 270, we get a radius of 5. Isn't that right? If we put a 270 in, that's -1, -2 times -1 is +2, and 3 make 5. So if we pull out our polar grid, then we have 3, 1, 3, 1, 2, 3, 4, 5. So if we compare it to this shape, the closest one, that's where our indentation is. The farthest one is opposite of our indentation. So if we think almost like a T, there's our T, or our cross. So if we think of our cross, ours it's going to be more like kind of not perfect, but kind of like that. Enough to get to the general idea.
That second part, we're probably getting, or if we're paying.
So that's on the formula sheet here at the top. So if we have one that's of that form, that's of the form A plus or minus B sine or cosine theta. So we just have to figure out our ratio, and then that'll tell us which one of those four shapes it is.
You're asking us to drop shape.
Yeah. It just depends. I mean, it could be just a graphic. So after you figure out A over B, you'll make a table of these 4 points, and those 4 points will give you enough information once you plot those 4 points, and you know the general shape of it, that'll tell you which way it's turned. Remember, our general one was turned that way, where when we graphed it, it was turned down. So the ratio of A over B lets us know which one of those is. The other thing that's kind of a standard picture is when we have sine or cosine with a number times theta. That's also going to be on this handout, so we'll do a quick overview. The cosine ones are not so bad because all of these are going to be what are called roses. If the coefficient of theta is odd, that's going to tell us how many petals there are. If the coefficient is even, then we have twice that many petals. So on ours, the coefficient of theta is 2, so how many petals? 4. Since that's an even number, we're going to have double that many petals. If we have 4 equally spaced petals, how many degrees are in a complete rotation? 360. If we have 4 petals, then that means each petal is 90 degrees apart. Right, that's right. Keep in mind that in order to get the tip of a petal, that's when the radius is the largest possible. So, like out here, that corresponds to a maximum radius. This corresponds to a max radius. I didn't make it. My pen locked up for a second. So, in order for our radius to be as large as possible, we want that to be as large as possible. What's the maximum value you can get for cosine? 1. So our maximum radius will be when cosine 2 theta equals 1. What angle okay, yeah. No, wait, sorry. Just this part will be 1. The whole thing, the maximum radius will be 2. This part will be 1. Because the most cosine can be is 1. So, at what angle, what's the first angle for which cosine is 1? 0. So that means our angle needs to be 0 degrees. So what does theta need to be so that our angle is 0 degrees? 0. That means our first tip, the tip of our first petal will occur at 0 degrees. So when we go to our polar grid, I'll give you the formula sheet. I'll give you this part, and then you can use that to sketch your. Okay. Do what? Oh yeah. Yeah, it doesn't have to be pretty. So in this direction, we're going to have a tip. So if we have r equals 2 cosine 2 theta, then in a direction of theta, in a direction of 0, we said cosine of 0 is 1. So what is our radius in a direction of 0 degrees? 2. So there's our first tip. Our first tip, we said, is going to be in a direction of 0 because 0 is what would make cosine 1. Well, if cosine is 1, that radius is 2. And then how many degrees did we say our petals were apart? 90. So if the tip of our first is at 0, then the tip of our second one is at 90. Our third one is at 180. Our fourth one is at 270.
Each layer is one, like that's 2 layers on top. Yeah. Right.
Yes. Yes. So that's a 4-starred rose, a 4-petal rose, I'm sorry. That corresponds to this graph. The first tip occurs at 0 degrees, and it has a radius of 2. Since this is 2, then we have twice that many petals, so 4 petals. If that would have been an odd number here, then whatever that number is, that would have told us how many petals there are. Now it turns out all of the ones we have for cosine, since cosine is a max at 0 degrees, the tip of our first petal will always be at 0 for cosine. The ones that are a little bit trickier are the sine ones. If we have r equals 4 sine 5 theta, if this is odd, then we have that many petals. So we have 5 petals. If they're so we need to find in what direction is our first petal. So in order for us to get a tip, that's going to be at our largest radius. So that's at whatever is the largest value for sine. What's the largest sine ever gets? 1. So we want to find out at what theta is sine of 5 theta going to be 1. What direction is sine 1? 90 degrees. So whatever we put in for theta, we need to get 90 degrees for that. So if we divide both sides by 5, we get 18. So that's our first tip. We put in 18 degrees for theta. 5 times 18 will be 90. Sine of 90 will be 1. So that's the angle for our first tip. So let's actually, I got a grid that's got that's a little bit more accurate. What do we have? R equals 4 sine 5 theta. So our first tip is at 18 degrees. How far out is it going to be? 4. At 18 degrees, we're going to have sine of 90. Sine of 90 is 1. 4 times 1 is 4. So in a direction of 18 degrees, this would be 15, so 18 would be a little bit more. We're out 1, 2, 3, 4 units. So 4, 18, that's our first tip. How many degrees do we say between petals? 72. So if we go 72 more degrees, is that 90? So at 90 degrees, we have another tip. If we go another 72, so 162, we have another tip. If we go another 72, what's that, 234, we'd have another tip. If we go another 72, 306, 306, we'd have another tip. And then if we had another 72, we'd be back to here. So we basically have something like that. So that's the 5-starred rows. It goes out 4 for each tip. So that's sketching some polar graphs. Once we sketch our graphs, then we need to do some calculus. So it turns out if we want dy over dx, this is where it gets a little confusing. So think of r as some function of theta. It's basically a parametric equation. We put in a theta, we get out an r. So in order to get our slope, I'm not going to derive it for you, but it's our function of theta times cosine theta plus f prime theta sine theta over minus f theta sine theta plus f prime theta cosine theta. Yeah, it does come from the quotient rule. If you think about that y equals r cos or r sine theta, and x equal r cosine theta, then dy dx, if we think about parametric equation, then dy over dx would be dy d theta over dx d theta. So if we take the derivative of that, divided by the derivative of that one with respect to theta, where r is actually a function of theta. So you take the derivative of that with respect to theta, so you'd have, it's actually not the quotient rule, it's actually a product rule. We use the product rule to take that derivative with respect to theta, that goes on top. We do the product rule to take the derivative of that with respect to theta, and that's the x theta, so that goes on top. So dy dx. So let's look at An example or two. Let's see, let's go back to this one. That's the one I want to do. Let's look at that one. 3 minus 2 sine theta. And let's try to verify that the slope at 270 degrees really is 0. So keep in mind, is f theta cosine theta plus f prime sine theta over minus f theta sine theta plus f prime cosine. And again, that comes from that y is r sine x is r cosine. So our r, which we're calling a function of theta, was 3 minus 2 sine theta. So we need r. We also need r prime. So f, which is r, 3 minus 2 sine theta. What's f prime? The derivative of 3 is 0. Minus 2, the derivative of sine is cosine of theta. So again, that's with respect to theta. So dy over dx is 3 minus 2 sine theta times cosine theta plus f prime negative 2 cosine theta times sine theta over minus the function 3 minus 2 sine theta plus f prime negative 2 cosine theta times cosine theta. So you give me an angle, I'll give you the slope. The angle we were looking for was what, 270? We were looking at what is the slope at 270? So at 270 degrees, let's just make a mental note. At 270 degrees, cosine is 0, sine is negative 1. Right? So when we substitute in for all these sines and cosines, we're going to put at 270 degrees, sine is negative 1, cosine is 0. So if cosine is 0, what happens to this term? That term is 0. If cosine is 0, this is 0. 0 times anything is 0. On bottom, we have minus. Let's see. If sine is negative 1, that's negative 1 times negative 2. That's 2 plus 3, so 5. If cosine is 0, that term is 0. So what do we get for that? 0 over negative 5, which is 0. Wasn't that what we thought the slope of the tangent line was? That's what we suspected. Let's look at this one. At 0 degrees, what would you suspect that the slope of the tangent line is there? Undefined? If I were to sketch a tangent line, I would suspect that the slope is undefined there. Let's check that. So dy over dx, I don't memorize this very well, so I'm thinking y, again, that's f times sine. So that's f prime sine plus f cosine. And they may have it backwards or the other way. X is f cosine. So that's f prime cosine plus f minus sine or minus f sine. And I got that just from calling this u and v doing the product rule. The derivative of this would be f times cosine. This times the derivative of that is f times negative sine. dy d theta over dx d theta. Function, what was it, 2 cosine 2 theta? We need f prime. What would f prime be? Negative 4 sine 2 theta? Yep, because it's 2 times the derivative of cosine is negative sine times the derivative of the inside. So 2 times 2 is 4 times the negative is negative 4 times sine 2 theta. Good. Y'all remember the chain rule. So our derivative in general is minus 4 sine 2 theta times sine theta plus our function 2 cosine 2 theta times cosine 1 theta all over minus 4 sine 2 theta times cosine 1 theta minus 2 cosine 2 theta times sine 1 theta. So we said let's check the slope at 0 degrees. So at 0 degrees, let's see, at 0 degrees, cosine is 1, sine is 0. So sine is 0. So we get 0 for this term. If I put a 0 in for theta, I'm getting cosine of 0, which is 1, times cosine of 0, which is 1. On bottom, I got minus 4 times, if I put a 0 in, I got sine of 0, which is 0, which means it doesn't even really matter what cosine is. But cosine of 0 would be 1. If I put a 0 in, I get cosine of 0, which is 1. Sine of 0 is 0. So what do we get on bottom? 0. We get 2 on top, 0 on bottom, which is undefined, which is what we suspected. So we can find, if we're asked to find when we have a horizontal tangent line, we have a horizontal tangent line anytime our numerator is 0. So the horizontal line has a slope of what? 0. So in order for this fraction to be 0, which part would have to be 0? The numerator or denominator? Top. If we have a vertical tangent line, what slope is that? Undefined. How is this undefined? At the denominator. So we could set the denominator equal to 0 and find out when all would that be undefined. That'd basically be solving a trig equation. Now, other things that we're interested is to find out when do we have tangent lines at the pole. Yeah. So basically, when does our tangent line go through the origin? So to have a tangent line at the pole, our radius must be 0. If our radius is 0 and our slope does not equal 0, let's call, instead of theta, let's call this as alpha. If f of some angle is 0, meaning our radius at that angle is 0, and our slope at that angle is not 0, then theta equals that angle is the equation of the tangent line at the pole. So if we think back to our graph, r equals 4 sine 5 theta. Let's look at when will that be 0? For what angle will we plug in and that be 0? So in order for this to be 0, that would have to be 0, right? So in order for that to be 0, if we think about the unit circle, sine is 0 here and sine is 0 here. So two answers to that would be, one of them would be whatever makes that 0. Another one is whatever makes that 180. So if we divide by 0, we get 0. If we divide that, if we divide by 5. If we divide that by 5, what do we get? 36. So those are two different polar tangent lines. If we go back to our graph, we are tangent to our curve at the pole at 0 degrees and 36 degrees. We go back and look at our graph. If I'd have done a better job of drawing this, then at 0 degrees, we should be tangent to our graph. At 36 degrees, which should be in here, we would also be tangent to the graph at the pole. So let's erase this. Keep in mind, if the tips are 36 degrees apart, then the place where we come back to 0 should also be 36 degrees apart. So every time we rotate 36 degrees, we should be back to being tangent at the pole. Not 30, it was 72 degrees, wasn't it? So every time we rotate 72 degrees. The tips of the pedals were 72. So every time we rotate 72 degrees, we should be. But at 0 degrees, we start out at 0 and we're tangent. And then we get to a tip and then we come back and we're going to be tangent. Then we come down to here. And if we were to draw the next one, if we rotate 72 degrees from here, then we'd be at 72 degrees, which would be about here. We would come back and we would be tangent to that line at the middle. And then we would. So basically the slope of this line is tangent to our curve right here. You'll see that. This line touches our curve at one point, and that point is at the pole. Because that's where our radius equals 0. And that's going to correspond to also where we're tangent. Which leads into a discussion. If we want to find the area of this pedal, we need to know where to integrate from. Which leads into how do we calculate area of a polar curve? We want to know the area of one pedal of r equals 4 sine phi theta. Well, how do we integrate a polar equation? Well, I'm glad you asked. So that leads us to 10.5. In 10.5, if we have a sector of an angle and a radius, let's think about how we would calculate the area of that. Let's say we have a circle. How do you calculate the area of a circle? Pi r squared. So let's see. If we were to take, let's say we had a radius of 1, what angle is that? 90 degrees or pi over 2. So let's just see. The area of that entire circle, if we had a radius of 1, what would the area of that whole thing be? Pi. So if we just want a fourth of that, that would be pi over 4. Now let's relate that to our angle. If our angle is pi over 2 and our area is pi over 4, what do we have to multiply our angle by to get that area? 1/2. Keep in mind that our radius was 1. If we made our radius 2, then our area of the whole thing would be what? 4 pi? If we divided that by 4, then that area would be pi. So if my angle is pi over 2 and my radius is 2, did I say that correctly? If the radius is 2, and the whole area is 4 pi, so that area is pi. Okay. Before I confuse you anymore, since we're short on time, I know what, I see where I want to go with that. It turns out the area of a sector there without having a lot of time, the area of that is 1/2 your angle times r squared. Think about the area of a whole circle as pi r squared. How many radians are in an entire rotation? 2 pi. So that's the area for a whole circle is pi r squared. If you want to break that in terms of a particular angle, divide it by that angle. Well, for a whole circle, the angle is 2 pi. So that backs out to 1/2 theta r squared if you tell me what the angle is. Theta over 2 pi, that tells you what portion of the whole rotation you have. If my theta is 2 pi, that's 100% of the rotation. My theta is pi, half of the circle. So we let our thetas cancel. 1/2 theta r squared. So what we're going to want to do is we're going to want to add, if we have some curve, we want to integrate from here to here, then we're going to break that into lots and lots of different sectors, and we're going to add all of those areas up. So it turns out we're going to add lots of 1/2 whatever our angles are times our corresponding radius for our partition squared. And we've seen in the past that becomes an integral where our change, if we let our change in theta get really, really, really small, the smaller our angle is, the better approximation that is. If we have a wide angle, then we might get too much area. If we get a really, really, really small angle, then each of those are going to be pretty good approximations. So the thing that's going to vary is our theta, so d theta, and then our r function squared. So that'll give us our area. Our limits on this, if this is d theta, then these limits will be in terms of angles. So it'll be between what two angles are we integrating? So if we look back at this one, we were tangent at the pole at 0 degrees and back at, so we were 0 here, then we went out to a tip, and then we came back to 0, didn't we? So this was, let's see, what was it, 0 and then 72? So we need to integrate that function, get to the end. So our area is 1/2 the integral from 0 degrees to 72 degrees, 4 sine 5 theta squared d theta. So that'll be the area of that one petal. Yeah, if we look at that graph again. Let's see, we started at 0, and then our first tip was at what, 32 degrees? 18. Was it 18? Just want to make sure I have that right then. So if we go from 0 to 18, that's the first half of it. So shouldn't, how far do we say between petals? 72. I'm drawing a, let's think. Okay, yeah. That's between tips. Each petal is 0 how many times? Twice, at the beginning and at the end. So if we start out at 0 degrees, if we put a 0 in, we get 0. And then when we got out to 18, we were at the tip. So if it takes 18 degrees to get the first half of the petal, then isn't it gonna take 18 more degrees to get the second half of the petal? It's 5 times 36, 180. Sine of 180 is 0. We were a little careless earlier when we said, well, if our tips are 72 degrees apart, then we do have zeros 72 degrees apart, but if you think about each petal is 0 twice, 5 petals, 0 twice for each one, that's 10, 360 divided by 10 is 36. So it takes 36 degrees to make each petal. So 36 degrees. We're actually going 0 to 36, not 0 to 72.
Why are you doing that?
Because we're wanting to find the area of that petal. The tricky thing about polar graphs is that especially if you have a system of polar equations, that really gets confusing because you could be at the pole and lots of different angles. So remember, for a rectangular graph, each point on a rectangular graph has one unique description for that point. But on a polar graph, we can name each point with an infinite number of names. For example, this point is a distance out 4 in a direction of 18 degrees. But if we add 360 degrees to that angle is coterminal, so it's in the same direction, so that's another name for that same point. What gets even more complicated is at the pole. There are lots and lots of times that we're at 0 degrees. The first time is when we put a 0. The second time would be when this equals 180. The next time would be when this equals 360. Then when that equals 540. And 720. Every 180 degrees, whatever theta would make that multiple, that would be the next time we're at the pole. Every one of those is another name for a point on the graph that goes through the origin. So sometimes it's difficult to find consecutive ones. So I guess one of the easiest things to have done there, if we would have thought about the unit circle, the first time that we're 0 is at 0 degrees. The second time we're at 0 is at 180 degrees. So when 5 theta is 0, and then when it's 180 degrees, those will be 2 consecutive points on our polar graph that we're at 0. So when theta is 0, also when it's, 36? So at 0 degrees, and then when we got back to a direction of 36, in a direction of 36, we're also out 0 units. So those are 2 consecutive times we're at 0 degrees. So in that are polar tangent lines that bound that leaf. 72 was actually the direction for the next one. If we go to 72 and go through here, our next petal is actually between this line and that line. It actually has a negative radius in that section because when you go from, if you put an angle between 36 and 72 in, you're going to get values down here and signs negative. So that's going to give you a negative radius. So that's going to correspond to being, let's see, in between here. So if we'd have gone 0 to 72, that would have actually been 2 petals. So to 72. But if it's symmetric, once we get the area of one of those petals, times it by 5, and that'll give you your total area. Yes. So 1/2 the integral from not 0 to 72, but 0 to 36. 4 sine 5 theta squared d theta. So that's 1/2 the integral from 0 to 36 degrees. 16 sine squared 5 theta d theta. We can pull the 16 out front and call that 8 times the integral from 0 degrees to 36 degrees sine squared 5 theta d theta. Remember we had a test on integrating trig integrals, and the rule was if we had a sine squared or a cosine squared, there was an identity we had to use. let's see, what was it? Sine squared of an angle. Make sure I tell you the correct one. It's either 1 minus or 1 plus cosine 2x. One minus. So this is 8 times the integral from 0 to 36. So if we call this x, this becomes 1 minus cosine of twice that angle. So if our angle is 5 theta, then when we change it to twice that, so 10 theta. Not 1 theta. 10 theta over 2. And we could put the over 2 inside or we could put it outside. So 4 times the integral from 0 to 36, 1 minus cosine 10 theta d theta. Now when we integrate 1, we just pick up a theta. Let's see. If we integrate cosine 10 theta, what would u be? U would be 10 theta. What would du then be? 10 d theta. So we've got cosine 10 theta d theta, so we need a 10 and a 1/10. So that's 1/10 the integral of cosine u du. I'll still got it. I'm just gonna integrate just cosine, and then I'm gonna take that answer times the 4. So what does cosine integrate into? Sine of u, where u is 10 theta. So we have our 4 out front here. When we integrate 1, we pick up a theta. When we integrate cosine 10 theta, we get sine 1/10 sine 10 theta. And we're going to evaluate that from 0 degrees to 36 degrees. Now, slight issue here. When we substitute in, it's okay to substitute here in terms of degrees. But here, we don't need units on the number we're plugging in. So if I put a degree in, doesn't that have units? What angle, what unit of angles is unitless? Radians. So we actually need our angles in terms of radians. So we need 0 radians. And if we take 36 degrees and convert it to radians, times pi over 180, pi over 5. So we get 4 times pi over 5 minus 1/10 sine of 10 times pi over 5. What is 10 times pi over 5? 2 pi. Minus 4 times, put a 0 in. 0 minus 1/10 sine of 10 times 0, which is 0. How much is sine at 2 pi? 2 pi is here, so what a sign there? 0. So that's 0. Sine of 0 is 0, so that's 0. So we're left with 4 times pi over 5. So 4 pi over 5. We have a 0 here, a 0 here, so that whole second thing is 0. So that's our area of one petal. So that was a little painful in that we had to have our graph. We also had to find the angles between which we integrated. We had it and to find those angles, we had to find our polar tangencies, which meant we had to find two consecutive times that our radius was 0. Let's do maybe 1 or 2 more problems, and then we'll call it a day. Just work on homework. And if you haven't taken the test, you can take the test. Huh? You don't have to. I won't count it against you if you don't, since this is the last day of lab. Yeah. And basically, we're just going to work problems doing that. Let's do this. I did. Okay. Let's find the area of the inner loop of r equals 2 minus 4 cosine theta. So we need to graph that. Once we graph it, then we can figure out what is this inner loop business they're talking about. So keep in mind, this is of that form, a plus or minus b cosine theta. So a over b is 1/2. So if we look at our sheet that I'm going to give you, if a over b is less than 1, we're going to have a graph that looks like this. So to graph that, let's make a table. Let's put our quadrantal angles in to begin with, and then we'll look for some more information if we need to. So at 0 degrees, cosine is 1. So what would we get? -2. At 90 degrees, cosine is 0, so we would get 2. At 180, cosine is -1, so we would get, what, 6? At 270, cosine is 0, so we would get 2 again. So if we graph this, then at 0 degrees, we go -2 units, which means in 0 degrees, we go away from 0 2 units, which away from 0 would be towards 182 units. Then in the direction of 90, we go 2 units. In the direction of 180, we actually go 6 units, which would be out to here. In the direction of 270, we go 2. So if our graph looks like this, notice the 2 points that are in line with each other, those correspond to the longest distance and then the tip. And then we also go through the origin. So if we translate this to this graph, And our graph is going to look like this. So when they say the inner loop, they want to find the area of this. So if we can find the polar tangency that'll correspond to when, if we integrate from here around to here, then it's going to add up all of that area. So integrate around there, we'll get that area. So we need to know at what two angles is our radius 0. So r is 2 minus 4 cosine theta. So we want to find out when is radius 0, not theta. So if we move the cosine theta over, divide by 4, we get 1/2. So let's see, if we think about our unit circle, let's see, cosine is 1/2. Cosine is the x, which is 1/2 of what, 60 degrees? Cosine is also positive down here. So that'll be at negative 60 degrees. 60, that's the same as what, pi over 3? Negative pi over 3, not 2. So we basically need to integrate from negative pi over 3 to pi over 3. If we go back to our graph, notice this line is in the direction of negative pi over 3. If we adjust this to correct, this is in the direction of pi over 3. So at pi over 3 to negative pi over 3, that's when we're in that inner loop. So we want to do 1/2 the integral from negative pi over 3 to positive pi over 3. Our radius squared d theta. So we have 1/2 the integral. If we square that out, we get what, 4 minus 16 cosine theta plus 16 cosine squared theta. The first one squared, twice their product. The second one squared. The product is minus 8 cosine theta, twice that, minus 16. Integrate this, we just pick up our variable, minus 16, integrate cosine, we get sine. And then to integrate that one, we got to do the identity. So instead of 1 minus cosine 2 theta over 2, it's 1 plus cosine 2 theta over 2. So for time's sake, I'm not going to go all the way through that integral. We've already done this part and that part. We've really done that part. So we'll stop there. The main thing is just knowing, okay, how do we find our limits of integration? We know to integrate a polar curve is 1/2 the integral of r squared d theta from theta 1 to theta 2. We just have to find out, well, what are theta 1 and theta 2? And that's going to depend on what area we're looking for. On that one, we were looking for that inner loop, so we needed to know where does that loop start and when does it stop. It starts when we're in a direction of negative pi over 3, and it stops when we get to a direction of pi over 3. Our curve basically started, if we started at in a direction of 0 degrees, we started here and we rotated this way. So from 0 to pi over 3, when we got to a direction of pi over 3, we were here. At pi over 3, we were at a radius of 0. So if we integrated from 0 to pi over 3, that would have done half of that curve. So then as we rotate on around, we're actually going to go, when we get to here, that's actually 300 degrees when we get back to here and then come on. Well, we don't want to go from pi over 3 all the way to 300 because that would encompass all of this area. We only want to go from, if we back up, negative pi over 3, then that's going to come around here to positive pi over 3. That'll take all of this area and then all of that. Or, like I said, we could have done from 0 to pi over 3 and then double that area. So that's going to kind of be the tricky part, finding how to set up the integral. So take a look at as many of those as you can for homework tonight. We're not going to do 10.6. We're just going to go through 10.5. So tomorrow in class, we're just going to spend time working on